So today, what I do, I summarize a little bit what I said in my previous lecture, and then I think we'll go to the subject what I promised in the abstract about vertex algebra and plane partitions and some combinatorics related, simple combinatorics related with this, but maybe just to say something about yesterday things. So actually our construction and our discussion was following that we had some vertex operator algebra with the following property. Suppose that in this vertex operator algebra, like in Clifford algebra, we have currents psi1, psi2, and so on, psi n, which are like just fermions. So they're all components as Q commute, or the corresponding set of generators which have psi I psi n here I, and here n. M belongs to Z. This is set of Fourier components, and this we can identify with Cn. These components are running in n position, and this M is here times C dz inverse. Anyway, like in Clifford algebra, I suppose that inside my algebra I have such things, and also similarly like we discussed yesterday in A, we needed to have at least Z2 grading such that elements psi IZ are odd. And maybe in algebra itself can be big and contain many other operators. Main example yesterday, it was one psi, but it has also psi prime, psi star it has, and also A, and A inverse. But in principle, it can be more general things. Then
do you also assume that there are some psi stars to not only psi 1?
No, I can or not. I mean, this psi can be part of some Clifford algebra there, or not. Maybe it's more complicated objects where we have not psi stars, but
But for your reduction to SL2 you need stars, right?
Need. Yes. But I'm only talking now about what we need to define screenings. And by screening, because this psi are like this, then inside this vector space, we can consider, say, finite dimensional subspace. W subspace here. And I want to take element from this W as screenings. So it means that if we take them, then we have the action of super algebra. Very simple in this case, also in this case, which is just odd space coincide with W, and subalgebra defining by W is invariant with respect to this action. Yes, and no, first of all, I want to say that this is special case, non-standard special case of standard construction from W-algebras, where standard construction is following. We have some big algebra, which is this A, and also some objects like this. They can be inside this algebra or in some completion or in some algebraic object which is a little bit bigger. And the object like here, the element from W acting by bracket. You take element A and send it to WA, where this is the bracket in more general things, W is some more generalized things. This object replaced by some version of Q bracket. And construction, so here is acting super algebra, but in general, some quantum group is acting on symmetries on vertex operator algebra, and the invariance gives us subalgebra. And so this is the way how vertex operator algebra acts. But in this case, some interesting things appear, which is the following. So we construct a collection of all W, as I said, is Grassmannian submanifold, Grassmannian manifold of dimension of W is some D of D dimension subspaces in this space, in Cn times Cz V inverse. Well, so it is some big, no, this is some manifold, and we can understand this manifold as the direct limit of finite dimensional Grassmannian, or consider a little bit different approach to them, but I do not want to specify. Anyway, construction gives us following. We have this Grassmannian manifold. This is big one. And in each point is leaving the stabilizer of corresponding algebra. And so altogether, we have bundle of algebras over some base. And now we can do the following. And the strategy of the following step is first of all, in Grassmannian, we have to take some open set. And because if space W is outside this open set, that stabilizer has bad structure. We do not like it. We first have to do that. But after we choose U, we can consider the vertex operator algebras of sections of this bundle over U, and no, for U we need actually some stability condition, and that is also, let us skip it. But sections is also vertex operator algebra, and by evident way it has center. The function on U, a center is this new vertex operator algebra. And so the result of this construction gives me the example of what was the vertex operator algebra with big center. Yes, and as I tried to explain in the end of my previous lecture, maybe not very successfully, that algebra of big center has very many applications in different parts of mathematics, even mathematics, because they appear naturally in Lagrange correspondence in constructing of an integrable system of Hitchin type. Yes, and they even appear in AGT business where they produce, as I said, like equations, and but
you're switching to isomodromic now.
No, it's a monodromic, but I think that my subject today will be slightly different from that. It's a monodromic deformation. I will say about this in the end if I will have time, probably not. I want to discuss the question how and what operator algebra appear in geometry. I mean in what is called a GT business, and this is a part of the story where we have natural construction of W-algebra when they appear with the basis, and this basis is labeled by some kind of plane partition. And such kind of vertex operator algebra, and the fact that such kind of vertex operator algebra sometimes also give us the big center, and this is because the beta ansatz things appear in this AGT business. This is interesting things, but this I only can mention. But first, let me explain something about W-algebra, which I will talk today. Well, and, the most popular example of W-algebra appear by the following way. First, let us take C star and let us consider the Lie algebra of differential operators on C star. Now, this is Lie algebra, and it has operators of first order, zero order, just product to Fz, F0z, which is a Laurent polynomial. In this case, it is commutative algebra, and it also has differential operator first order, like this, and operators of second order, it is like this, and so on. And first of all, this is the algebra, but we can make the algebra from that just by operation AB minus BA as differential operators. Yes, and so this is Lie algebra. And for example, this part is the algebra of vector fields on a circle, and in here, if I take Li B equals Di plus 1 d over dz, then we have famous Virasoro bracket relation that without central expansion. Li, Lj.
This is with algebra.
Oh, it is with, but with I is running from minus infinity to plus infinity. Still with algebra. With.
Virasoro still reserved for central.
Yes, anyway, here this is, in this case, it is G minus I with I plus J. Yes, and well, so this is the algebra of differential operators, let us denote it by D. And this algebra has first of all, first things, it has central extension. Which probably it is not reasonable to describe, but I want to say that in this central extension, which I denoted by maybe like this, in this case, subalgebra Li generated by Li, it becomes Virasoro algebra. So in a central extension, it is still this, but it is appear the extra term. Delta I plus J0, and we have here I cubed minus I over 12, and here some value of C. And no, formula for central extension can be, in principle, can be written, and it is interesting, but maybe not now. And this commutative subalgebra in central extension, it becomes Heisenberg algebra. It means that if Hi be equal to Zi, then in this case Hi, H minus I will be equal to I, and here it is can be some coefficient, and all other H's are commute. Yes, so this is Heisenberg, and this is Virasoro. And what else? That such algebra has a representation, class of representation. This class of representation can be characterized, and in representation theory, it is some version of category O representation with highest weight, but at least in these representations, operator HI gives us acting and gives us a representation of Heisenberg. It means that a representation of Heisenberg, such, for example, here it is always some vector which is killing HI when I is positive. And similar story with L. Representation has such vector. So it means that it is some conception of creation and annihilation operator. But for me, no, it is important, but for me also important that such kind of Lie algebra can be considered as vertex operator algebra. So, for example, we can consider HZ.
You don't understand HI W, what is the meaning of this? What is W? Some words?
Where?
HI,
No, I just said a few words about structure of this representation. Structure of this representation, it means that category O. So it means category O for irreducible representation of Heisenberg from the category O. This is representation just H. This is a representation where we have highest weight vector, which annihilated by this, and H0W is equal to some lambda W. And for example, the representation from category which I am talking after restricting to Heisenberg is the direct sum of such representations. And if you are talking about restriction to Virasoro algebra, surely they are not so simple. But generally they be, for general parameters, it is direct sum of Fermat representation, and in general, they belong to category O for representation of Virasoro. Anyway, I just said that it is some reasonable class of representation of this algebra, and this we have not time to discuss it in detail. But anyway, I have HI, and I can introduce the generating function of this HI, T minus I. And I can also write down T, this is Li times T maybe minus I, or maybe here usually 1, here 2, but let us do not take care about this. And also, for example, let Si be component of this. So Si is corresponding to Z I plus 2 over d over dz square, and so it is some st which are generating function of them. So all of them we can consider as generator of some vertex operator algebra. It just have a standard meaning that correlation function, as I expected, as I explained, of such kind of operators, they are rational functions, and it is conception of operator product, and so on. And it means, for example, that I take this st1 times st2, it is starting with t1 minus t2 minus 6 times some constant plus lower terms, so it is just vertex operator algebra in a standard meaning. So, well, and if you are just discussing the representation theory of this object, then it is closer to Lie algebra business. It is not necessary to take in mind vertex operator algebra things, but you see, now the next step of the story is following. This is Lie algebra, but we get this Lie algebra by following way. We took differential associative algebra of differential operator and consider the operation AB minus BA. So from this point of view, it means that this algebra is some version of GL infinity. So because any differential operator is some kind of matrix of special type, surely, but or so because it is some version, it is the following idea. So if we have GL infinity and have universal enveloping of this, then such kind of algebra can be deformed in a quantum way and get a family of algebras depending in some parameter q. And it is good things that such kind of deformation we can do with many Lie algebras in infinite dimensional case as a situation rather interesting and produce interesting examples. But anyway, the statement is that we can take universal enveloping of this central extension of Lie algebra of differential operator and then introduce some kind of deformation depending in parameter h. How to do it and what kind of machinery behind that, I cannot explain, but I want to say that this is it. And the result is can be understood as deformation in class of algebra of differential associative algebra, but better to do it in a class of vertex operator algebra. So this is a family of vertex operator algebra, and actually, no, it is not Q. It is not Q vertex operator algebra at all. Parameter Q in order not connected with this business, I replace Q by H here. It is no difference operators now, nothing like that.
Operator products are not very reasonable now, right?
No, it is reasonable. It is still reasonable because in this deformation, I will say something about its structure, but at least after deformation, Heisenberg will be still Heisenberg. After deformation, Heisenberg survive. In deformation, Virasoro also survive, and it will deformation. But what is changing? That in this universal enveloping algebra, I take this generator, and if I calculate bracket, so what we take? We get bracket of two elements from here, give me something here, and lower terms also. And but after deformation, bracket of two elements from here, say Si and Sj, give me this term, but not only this. It gives me something quadratic in terms of this and that. So it means it will not be Lie algebra, but this is deformation of this as associative algebra, where we deform it by this way, just adding some quadratic, in this case, just adding some quadratic expression in generator. And people who knows this the structure of Yangian type algebras, this is more or less the same story. In Yangian, we start with current algebra and Lie algebra, but then deform it such that standard for bracket relation for standard generators, we add some quadratic term. A similar story is here, and really this is some analog of Yang.
Q story, this H story. Q story, you will get Q Virasor.
Yes. This is H story, and this is vertex operator algebra. Q story, you go to some. No, Q story in some sense is necessary, and I will mention something, but no, it is just more complicated. So first, just to claim that such kind of deformation really exists. And maybe one more thing, that if you consider the representation of these algebras, in this representation, you have two main parameters. One parameter is this parameter H, which has just claimed that it exists. But second parameter, that we can normalize generators here, such here we have just I. But after that, some more parameters appear, because here we have C. And this C is some main parameter, which one of the main parameters which characterize our situation. So it means that the representation theory of this algebra, surely it has H and also C. It is reasonable to say that algebra itself depends on two parameters, in H and in C also. Yes, and now
are we approaching W-algebras, or just some kind of independent story about deformation of the algebra whole U of differential operators?
Sorry.
Is it connected with W-algebras, or is it just some kind of different track?
It is different track, but it is connected. And
you mentioned Virasor remains Virasor.
Yes, and no, this algebra is very interesting because of many reasons. One reason that they can be constructed as vertex operator algebra by many ways. And I want to say something. Yes, and the idea of what I'm talking is following, that one way to construct vertex operator algebra, we want to build them from some more simple or more handleable vertex operator algebra. And in this case, we know that if I have G, semi-simple finite dimensional algebra, I can take the current algebra, consider the central extension, and this is algebra G hat, and G hat, or universal enveloping of G hat, can be understood as vertex operator algebra, which appear in conformal theory business, in Versumina series, and so on. Yes, and most of the construction of vertex operator algebra, they have the following structure. They are either some subalgebras in such universal enveloping algebras of G hat, or we can construct vertex operator algebra from such kind of object by reduction. Or a screening business, this is a similar story. We can take this vertex operator algebra and define the action of something like my fermions. Actually, in reality, it is some quantum group, and taking the stabilizer, and it is also constructed of vertex operator algebra. And then I want just to examine the construction where we get just this, the formation of algebra differential operators. And such construction are the following.
So example, this name for this topic, example of W-algebras somehow disappeared, right? You decided not to do it now, right? W-algebras will consider later, right? Or you decided just to skip to stick to differential operators?
No. W-algebra, it is W-algebra, this is a result of construction of either reduction and so on from the no, so okay, wait. So now let me formulate something. That first, let me say something about famous construction of W-algebra related with, no, W-algebra related with any semi-simple real algebra, or what considering W-algebra which relate with GLN. And it is famous because it is working by the following OGLN if we take SL2 hat on this position. Then result, the famous construction is following. I can take this universal enveloping, then make up some reduction, and get as a result Virasoro. And if what kind of reduction I will discuss a little bit, but it is just some sort of killing some generators here, and the result gives us Virasoro. Anyway, it was very old, but also then Zamolodchikov took first universal enveloping and SL3, and he produced some generalization of Virasoro, which he called W3 algebra, and the name of this standard name is Zamolodchikov algebra. And surely after that it is possible to take GLN or SLN hat, and for me it will be important to work with GLN. Right now it is not so important, and it gives us some family of algebra of type WA.
Yes, knowledge we use some kind of PRST machinery. So what was
no, he did not use it.
But he obtained some closed algebra, real algebra, right? So, what was his approach? I don't remember.
No, in his approach, no, actually, no, if you're asking me what actually Zamolodchikov did. He did not use any reduction. He did not use the even screening approach. He made Zamolodchikov because he was very, and still is very good in calculation. He did the following things. That conformal field theory and all this business based on Virasoro algebra Li with the relation which I wrote there. But because it is conformal field theory, that it is natural to examine something where bigger algebra are active. And surely such kind of algebra, it was known from the very beginning, it was super algebra. And this super algebra, her name is Navier-Schwarz super algebra. And this kind of algebra, like Virasoro, appear in the string theory. And the structure is following, that in this algebra we still have Li, but additionally we have some generators, maybe G3. And these generators are odd, and the main relation, I do not want to write all relations, but main relation that G3 plus, which is Q bracket, is just Li plus J. Now, if you do it, you can, and also it is some simple relation Li with Gj, which gives us Gi plus J with some coefficient. No, well, this object is super algebra, which is symmetry of something, and it is working nice, and because in string theory we have the odd degree of freedoms, and something has to act there. And first example, it is this. But his question was following. Can we generalize it? Can we just add here some generators as J, which are not odd but even? And he chose this generator, which are because of some reason. No, in the algebra of differential operator, we have Fz, d over dz, and we have some gz over d over dz squared. And he chose these generators, which bracket of this with this are the same as my D algebra. And it means that he chose conformal weight of this as G equals 3. And he wanted to generalize this. And after some calculation, he found that it is the only way to do it. So we know bracket this with this. But he tried to understand what can be this. And because of associativity constraint, it is some condition that this has to be equal the sum of L alpha, L beta, alpha plus beta equal I plus J plus some additional term, linear one. And this is what just he discovered by calculation. And it was nice algebra, and he surely some kind of conformal.
It must be cubic differential operator, cubic. How it can be?
No. In his case, he did just this. He had not in mind any connection with the algebra of differential operators, nothing like that. He just understood it as a generalization of this.
So those other can be L is L and S is S, and it is just a matter of calculations.
Yes. Okay, but...
So he knows the relations between L and S exactly from differential operators?
No, about differential operator, he did not care. He wanted to generalize this. This was his goal. And anyway, if you just want have such ansatz that in algebra we have this, and you know, break it with them, then result of calculation that Si and Sj, no, it can be zero, but it is not interesting. If it is non-zero, then it has to be like this.
No, he wants to obtain close relations.
Yes.
And check by hand when it is close. It's involves some.
No, it is usual story. You need to discover such things. You need two kinds of ability. To calculate very good, and you need intuition just to believe that such object exists. And he was such guy, and so he did. Anyway, only later, soon after that, but later it was discovered that such kind of algebra are getting by reduction from this, and now I want you to follow. Let me just say idea of reduction. Yes, and so the idea of reduction, technical details are complicated, but the idea is simple. If you have algebra A associative, and if you have associative subalgebra B, then we construct the new algebra from that by the following way. Let us consider some representation of B. In example, this representation is finite dimensional, but it is not necessary. Let us take some representation of subalgebra B. If we have associative algebra and subalgebra and representation of subalgebra, then I can consider the induced representation. Induced representation, let us write it. R is representation B, and we are induced to A. Yes, and the reduction, which is given by this way, if I have such induced representation, I have algebra of homomorphism of this representation to itself. So I can consider the algebra of Holmes from this induced representation to itself. Yes, and it gives us surely the algebra. And for example, if B is just trivial subalgebra.
A homomorphism or B homomorphism?
A homomorphism. A homomorphism, yes. And surely it is clear that, for example, if B is trivial, just consisting in zero, I do not insist that subalgebra has unit. And if I make up induced representation from trivial representation of this zero, then induced representation will be just A. The homomorphism of A to itself is A. If subalgebra B is bigger and R is trivial, is one-dimensional representation, then the space of homomorphism is smaller. And it is by this construction we can get interesting algebras. And surely this construction of direct counterpart of construction of Gekke algebra. Because if I take as A is a group algebra of J-length over finite field, and if I take as B group algebra of Borel, but group here it is just such matrices. Yes, and if I take as R trivial representation, then the make up this construction, then the result give us usual geek algebra, where this is finite field, this is depending in Q, and so this is geek algebra, and so it is reasonable to call all kinds of such constructions that generalize geek algebras. So it is rather natural construction. So, well, it means that I can play by this construction by many ways. One way, I can take A as a universal enveloping of JLN, for example. And I can, in some sense, I can try to repeat what I said about JLN over finite field, but for finite field, if we study what is called cuspidal representation and things like that, people take, for example, JLN over finite field, but as subalgebra, they take group algebra of this group, maximum unipotent subgroup, and as a representation, they take non-trivial character here, and then they study the endomorphism of the corresponding algebra, and this is very important step in classification of representation of JLN over finite field. So you have to do it to know what is this if you want to say something about representations. And this construction is so, and as a construction of new object, it is very popular. We can take as a universal enveloping of JLN, for example, and B universal enveloping of maximum nilpotent here. And we can take character, non-trivial generic character of this n, one-dimensional. And we can try to do this. And in this case, such kind of construction, this is constant theorem, which is said that the algebra of endomorphism in this case give us a center of algebra, surely, but it is isomorphic to the center of universal enveloping of this. And this is also very, if you put here, for example, the superalgebra and so on, it is some counterpart. Yes, and the important point that it is rather interesting to do it in the case of current algebra, but it is not so easy. Anyway, it is possible to do. You can take universal enveloping of JLN hat. You can take universal enveloping of n hat. And so hat, it means here, for example, it is n times c gz inverse. Yes, and you want to repeat this construction. It means that you take this non-trivial character of this, you take induced representation and take the algebra of endomorphism. But because you want to get as a result vertex operator algebra, you can adjust the construction of induced representation to get vertex operator algebra. And it is possible to do. The construction is basically the same, but function of induced representation, we have to replace to so-called semi-infinite. Induction why it is so semi-infinite and how to do it, let me skip it and do not discuss. But it is important to understand that the idea is just the same. But, so construction is working, and it is important that it produce vertex operator algebras. And let me say few words about
what is the answer if you take straight construction or semi-infinite induction. So what is the answer for the algebra? W?
Yes, yes. It is one of possible construction of W-algebras. Yes.
Will be exactly WL?
It is exactly. So if you do it for SL2, you get as a result Virasoro algebra.
For semi, what if you ignore semi-infinite and take?
If you ignore the semi-infinite and just make the usual induction, that surely no, the algebra of homomorphism of such object is ill-defined, but at least it cannot be vertex operator algebra.
But still, what is it? It is well known.
No, in this case it is ill-defined. If you do it, for example, for the group over Bldg fields, then it's okay. Then it's okay. But in this algebraic context, it is impossible, and you need to modify the construction of induction.
What is the analog of constant theorem in this setup?
No.
Finite dimension, three-dimensional constant theorem, center.
No, let me say, because if we are talking about this, no, I mentioned my lecture that, for example, if you take SL2 hat for K, SL2 hat depending in level. If I said if level is equal -2, then in this universal enveloping we have big center. In this case, constant theorem is literally survive. So it means we make up reduction, and reduction just coincide with this center. And center is some commutative algebra. Semi-infinite induction, because center, if it exists on this, if we understand it is the vertex operator algebra. If we just understand it is usual Lie algebra, then no center, and it is also not good. But in this case, it's okay. Anyway.
And if it is not -2, then what is the answer?
No, the answer is -2. It means what? That it is center, but I can make up changing a little bit, or maybe not little bit, but I can change this, and then. But in this case, this reduction gives us some vertex operator or algebra, which can be understood as a deformation of what we have for -2. So for -2, it is.
W-algebras?
It is W-algebra. It will be.
Don't say it. Why you need to push it to say this? What are the problems?
W-algebra.
Why epsilon is necessary? Is it correct that it's just to take any central?
No. It is no. For any epsilon, we get W-algebra, and for epsilon 0 for -2, we also get W-algebra. What can? No, for SL2 it is Virasoro, and for Virasoro the situation is following. That I'm saying that in general, for K result of reduction, give me universal enveloping of Virasoro. Where central charge depends. Yes, and central charge depending in K. When K go to -2, then this central charge go to infinity. And to infinity, it means, from the point of view of Virasoro, what is calling quasi-classical limits. So it means that universal enveloping of Virasoro degenerate to commutative algebra, which is just the center. So this is what is going on in this situation. And,
so it is for SLN. What about other root systems? So same.
No.
This is literally Hickey type construction, right? Classical story about Whittaker
No, wait a moment. No, this is just construction of Whittaker, and people like Denis, Gitzgoyer, Lurie, maybe they make this kind of consideration closer to the standard Whittaker business.
But does it literally Whittaker construction?
No, there are a lot of technical details because it is not completely the same, but it is very, very close. Ideologically,
semi-infinite deduction is okay, no problems. I understand what you mean here, but anyway, some kind of semi-infinite H product, right? So what can we do?
No, let me wait for a moment. So let me just say one thing.
We have a theorem, at least for GLM. It is literally W-algebra.
It is literally W-algebra.
Why you mentioned Gitzgoyer, Lurie, so...
No, Gitzgoyer, Lurie, and also this is the question what to do with this construction after that. And then it depends who is doing and what he wants. Anyway, one word before.
So you refused to discuss other root systems. So you mentioned it is only for GLM, special feature of GLM.
No. It is working in general.
In general. So we have W-algebras.
No, well, so general definition of W-algebra, which people study, it can be following. Here we can put, in principle, any Lie algebra of superalgebra. In this place, it is possible to put not necessarily n, but some good or some or in general arbitrary subalgebra in nilpotent. And like chi, we can take character of this.
Why you can take just n, classical n, which is exists by definition of GK?
No, but we can take a smaller subalgebra if you want.
Why you need to take smaller?
No, but even in periodic business, it is reasonable to considering smaller subgroup in unipotent group, and people do it. It is also necessary.
But you claim is take upper triangular matrices, but parameters can be arbitrary powers, positive and negative, right?
Yes.
So it is essentially detective stuff.
Yes.
Right? Yes. So what is better to take?
No, nothing bad. Nothing bad. But what I want to say that if you are working with periodic group, then as first approximation, just repeating finite dimensional case and taking Borel, you get as a result a fine Gekke algebra. Yes, if you take as a subalgebra nilpotent algebra and taking, say, character and so on, or even not taking character, as a result we have bigger algebra, which contain also in some sense Cartan. So this is a sort of your algebra because it is double. Yes, and so we can get it by this way.
If the character is generic, right? Generic character, right? Then it's okay. You can take the whole thing, right?
Yes. Or if it is also interesting to take, for example, GLN over periodic fields and taken unipotent group and taken subgroup in unipotent group. Yes, taking character, and in this case, it gives you also some version of our object, and it is also interesting to study. So all such story is working and exists in a fine case and gives us collection of the objects traditionally all of them are calling W-algebras.
Are they exactly W-n algebras?
No, they're different. It depends, surely it depends what subgroup is there. But if U is n is maximum nilpotent, it gives us W.
If we employ other approaches like BRST, will it be
BRST it is BRST it is not other approach. It is the same approach because if you want to determine what is semi-infinite induction, you do not need it. But actually, semi-infinite homology and things like that, this is very important and natural tool in this business. Anyway, let me continue a little bit. So I explained the reduction, and what let me add one thing, that what is going on, that if I said that if I take universal involvement of G and take nilpotent subalgebra and take character, generic character, according to constant.
Head.
Yeah, but first before head. Before head it is center. Center has some generators and Casimir operators. First Casimir, second Casimir. For GL3 we have usual Casimir and cubic Casimir, but let us put here their degree. For GLN is 2, 3, 4, and so on. And if we put this and this K2, K3, K4, and so on, they become the generators of vertex operator algebra. They become dependent in T now. And if we put here, for example, JLN, that we have K1, because we have central element of degree 1. So we have only K1 depending in T. Yes, and the construction is working by this way. The result of the reduction gives me W algebra, which has generators. And these such elements are in correspondence with central element.
There will be only one key for SLN, right? Because degrees are uniquely defined uniquely, this guys here. Generally, it will be some families, right?
No, generally depending on exponent
but
of
you collect K1, K2, K3 in one family, if I understand you correctly, or it will be exactly
No, I do not want to. In families, I want
repeat what your claim about GLN. So,
no, about GLN, I said that center
K1, K3, right?
K3 and so on. The last one for the GLN is Kn. Yes, and as a so if you are talking about critical level, it will be just some commutative algebra with such kind of generators. And they are, before it was just K1, K2, K3, in affine case, all depending in T. So generators are now Fourier components of this in T. Yes, and after deformation, it means if we take non-trivial level here, then it will give us some associative algebra or vertex operator algebra with the same generator.
May I ask you a genuine question? So for you, it seems that for you, vertex operator algebra is just some nice way to arrange relations between your generators here, right? And then relations are nice, and after this, relations have some physical CFT meaning here, right? Do I understand correctly, right? You don't really need them. You need relations between generators, which are coefficients, so to say, right? But on the other hand, something happens, and because they can be presented in a nice way using operator expansions, right? So, what can you continue and say what is important if you can really have some nice formulas in terms of some generator parameter T, whatever, right? Is it physically important or mathematically important?
No, it is just some algebra. Anyway, you need to know.
What is important about the fact that you can arrange relations, just algebraic relations between generators, arrange them in some operator expansions here? What is exactly I can do a representation here of Virasor without any mentioning any conformal field theory, right?
No, you can. But no. But describe the result of this construction without this language. Theoretically possible, but completely unnatural.
Why? Virasor is
Virasor it is possible, but one thing that in the mallogical description, if you are working with such kind of relation, it is summation L alpha, L beta, alpha plus beta equal I plus j plus something. This is main relation in the mallogical algebra. No, main problem, no, why not? You can work with this. One problem that this sum is infinite. No, it is not big trouble. Infinite and infinite. But VOA is finite things. It means that operated product as V as W, it is Z minus W, maybe minus 4 plus Z minus 2. Here we have TZ, where TZ is generating function of this, and maybe we have some more things here. And here is TZ square is here. Yes, and here is also some coefficient. So this expression of the operator product is finite.
But if I need representation theory, it will not be very helpful.
It is helpful. It is helpful. Yes. Now let me continue a little bit because I cannot formulate it. I want for several minutes to do it. Anyway, my generators are like this, and if it is for J-Len, but if n go to infinity or become big, we get infinitely many of generators because now center of J-Len has such kind of generators, and I want to say that this algebra actually is isomorphic to my quantum deformation UH of this central extension of Lie algebra of differential operators. And no, naively, its correspondence is what? So this corresponds to differential operator of first order, this corresponding to of zero order, this corresponding to first order, this corresponding to third order, and so on. And the situation is the following. So we have this algebra, and if we send n to infinity and appropriate way make with C, then in the limit we find out the universal enveloping of this Lie algebra which we are talking about. No, this fact is known for maybe 20 or more years, but it is completely non-evident. So why it is happening by this, it is not clear. But anyway, the fact that it is explicit construction of this.
What is non-obvious to me, absolutely obvious. So you need to use here semi-infinite induction or equivalent BRST technique here. And why it is really the output is so simple, it's not clear, right? That's what you mean, right?
Yes, yes.
So
it is one question, and the other question where this Lie algebra of differential operators is hidden in this construction.
Because all cosmology can be embedded into GL infinity in some sense, right? This is trivial, right? But this is not trivial because there are some extra steps here. Like semi-infinite induction.
No, let me say a little bit more about the situation. So, well, no, to explain all details, it is not easy, but I want to say some notation which people using for W-algebras. So again, let me add again one more thing. So W-algebra, which I construct here, you see the construction use GLN U, and GLN has level K, and also, so I make up after that a reduction and get some algebra which has such set of generators which are ending on n, because center is like this. But if you look to this algebra, then and look structure constant of this algebra, then you find that they are algebraically dependent in n and k. Therefore, you can consider actually some algebra where n and k are parameters. And no, k is k, here k is arbitrary, but n in such construction is fixed and has to be positive integer. But in reality, you can make up analytic continuation in n and get a family of algebras.
You mean differential operators when it is not about polynomials or about what? About arbitrary functions? Operators are still differential, right? But still functions.
Again, for any n, especially, and in the case if n is some complex number, this algebra is deformation of universal developing algebra or corresponding vertex algebra of this differential operator for some h. And because I cannot explain who is h because I do not explain how.
But still, is it connected with the possibility to consider vector fields which are not polynomial? Some more general. Is it connected or it is just something absolutely impossible to explain?
No.
It is impossible to explain.
No, it is not. It is not connected with this. Again.
Instead of n, which makes perfect sense here, right? You make arbitrary real or complex number, right?
No, and it means it means the following, that it is a very familiar situation that algebra GLN, it cannot be defined in the case when n is complex number. It is impossible.
You know very well that it's possible for Bldg and some other projects.
Yes.
Right?
Yes. So you can
categorically
you can define tensor category of representation of GLN, and there introduce the n be complex numbers. And so the situation how it is working here, it is close to this approach. You get some result, you get some algebra which is depending in n and t, which can be understood as the reduction of this GLN head of level k, where n is complex number. And this algebra itself does not exist. And if you are talking about representation theory, this is the question. How can we do it in this case? In this case, I do not know how, and nobody knows how to make up this delineation.
You mentioned you can define this algebra. Just 5 minutes ago, you mentioned that you can define. Now
I did it.
That you cannot define this algebra. Only representation theory somehow exists, right?
No. Again, I can define this.
Can you define W-algebra for any complex number instead?
I can.
You can. You mean the relation generators?
Relation and generators, for
Yes,
example.
Do we need this construction GL infinity for this, or it is something different?
No,
you don't need stabilization, right?
No.
How can you define then using what? Using some deformations of relations, or what is corresponding? Whatever geometry, algebra.
No, there are several ways. One way how you.
What's your favorite way?
My favorite way to write down this algebra by generator and relations and see that in these relations we have polynomial dependence in n and k. That's all. But it is not the best way, but straightforward way. About such W and algebra, there are some kind of notation, and these notation are not very natural, but maybe some you know that, for example, for Virasora algebra, there are some class of representations which are labeled by two relatively prime integer, and they produce minimal models. And these parameters P and Q are in principle integer for minimal models, but they are good parameterization of the algebra. And for example, Wn algebra, it also has minimal models. Maybe it is good just to mention it. Such minimal models are labeled by two numbers, P and Q, which are relatively prime, and key here. And for example, for Virasora, central charge minimal model is given by famous formulas like this. I think everybody saw these formulas somewhere. And in JLN case, the central charge is given by the formula K minus K square minus 1 times K times P minus Q square divided to BQ.
But where is that? No n at all? Only
Now K. Now
K is n.
no,
K is number, which is n.
K is n, yes. Yes, and so this is central charge. I want to say that algebra depending in K and C, but better to say that they depending in K.
So when K is 2, we will get exactly the old formula, right?
Old formula plus 1, because it is J2 case. Yes. So the structure of this formula is what? Here is K, here is the dimension of SLN, here we have also this K, and we have this.
Because somehow PQ are connected with L0 and L1 in Virasora, and what is W-algebra? Do we have some remarkable elements? Two of them like L0 and L1?
No, role of P and Q is not so easy to explain. Maybe only good to mention that if you look to a role of quantum group or screening or things like that in this business, then their relations usually are written in terms of P and Q. So because of this, P and Q very important tool for that. Yes, and then what I want to say that so maybe even this moment it is possible, reasonable to mention something about geometry. Geometry, geometry it means the following, that each vertex operator algebra and anarchy algebra also characterized by so-called vacuum representation. This is the simplest representation which my algebra has, and again, the operator state correspondence says that vector of this representation is in correspondence with vectors in this representation. And let me say that I want to say two things. That suppose that KC, and I said suppose that KC are generic.
Just one more question. So are these PQ are connected with epsilon 1, epsilon 2, I mean, AGT business, epsilon 1, epsilon 2?
Yes, yes.
So there's some algebraic formula, right?
Yes, yes, there are. But KC are generic. Then vacuum representation, this first, it is graded space. And the character of this graded space. No, it is graded because grading is natural. In my algebra, I have HI, which has grading I, Li, which has grading I, and so on. And so because of this, representation also has a grading. And character of this graded space is what? It is 1 minus Q, 1 minus Q square square, 1 minus Q cube cube, and so on. So it is given by famous Mark-Magon formula. And now if you what kind of representation is this? No, because I said that W-algebra is the deformation of algebra of differential operators, mean and differential operator also vertex operator algebra. So we expect and really want that this algebra has representation of such kind. And the strategy of the construction of vacuum representation for this with this basis, it is easy. Okay, so I have ring of polynomials and Laurent polynomials and D. No, I used such D, I see. The algebra of D is acting here. Then we have a map from D to J infinity, which is acting here. Yes, and
what is this graded space? So polynomials, I can't immediately identify it using the character Mahon formula. What's polynomials in terms of what? I mean, what is this vacuum representation? Graded what? Graded, yes, it is graded, but what is exactly the model for this space? Linear algebra.
no, maybe I.
Will you explain?
No, I try. I try to explain.
Exactly what is this linear algebra structure of this space, right?
Wait a moment. That such kind of space, the algebra of differential operator, also we expect it to have such kind of representation. And my W algebra, it has to be some deformation of this. How to construct the representation of algebra of differential operators?
So this is the character of the differential operators. This is the character of all differential operators.
This is the character of representation, some representation of algebra of differential operators.
Acting where? In some polynomials, which representation?
No, this representation, let me say, I'll try to explain. Anyway, algebra of differential operators has embedding into J infinity. J infinity has natural basis Eij. So, but differential operator surely gives us the infinite combination of Eij. Let us forget about this in a moment. Anyway, Cartan algebra is Eii, and Eij, where I is less than J, is upper nilpotent, and the Eij opposite is lower nilpotent. And then algebra J infinity, it has irreducible representation with the highest weight lambda 0, 0, 0, 0, 0. No, highest weight is the number of how EII is acting on a highest weight vector, and we can do it. I suppose that, for example, E00 is acting by 0, E11 acting by 0, but E minus 1 acting by lambda, and so on. No, lambda is some generic parameter.
Parameter, right?
Mm-hmm. Yes, and if we consider the representation, irreducible representation with this highest weight, how to understand what is this? For that, we have to draw maybe here the infinite matrices. EIJ are living here. Yes, and my EII are on diagonal. And so highest weight that all these are acting by lambda, all these are acting by 0. So it means that my irreducible representation is induced from representation of this parabolic algebra. Yes, and if lambda is generic, then this induced representation is irreducible, and because it is irreducible, this is, as a representation, this is polynomial ring in what? In 0, 1, in E. This representation is polynomial ring in this. Yes, and because this is polynomial, now about how we calculate character. Character we calculate the, so what is here. It is infinitely many variables, and degree of this is 1, degree of this is 2, degree of this is 3, and so on. And therefore, if we look to this representation, we can easily see that the character has Mach-Magon formula, but it is not Mach-Magon yet. But anyway, what is going on now? That algebra D is embedding here, but it is embedding actually not here, but it is, differential operator is going on to infinite combination of this EIJ. So if you actually want to determine how this infinite sum is acting in this representation, you get central extension. So really, this algebra is acting, but it is some anomaly, some correction, which is simple one, and you get the central extension. Yes, and then what is also possible to say about such kind of representation? About such kind of representation, it is possible to say that as a lot of other representation, this representation has a basis.
What are K and C? Here there is no K and C.
No, first of all,
you mentioned
yes. It means that because it is Lie algebra limit, it means that the parameter k we send to infinity. But parameter c survive, in a sense. And this parameter he is more or less this lambda. Not precisely, surely, but at least it can be expressed in this lambda.
You mean C and lambda are connected, right?
C and lambda, no, C survive even in this Lie algebra limit. And here we can get such representation. We can see the action of Virasoro subalgebra in this differential operator, and we can just calculate how Virasoro is acting. And as a result, we get some central action of central element, which depends in this lambda.
But for AGT, you need sketch. You need to go to finite level, right?
No, for AGT we need something, but AGT has its own problem, but a little bit later, if I can say something. But about this representation, if you take finite dimensional representation of GLN, then in such representation we have Girfan-Zeitlin basis. And in such kind of representation, we also surely can determine some version of Girfan-Zeitlin basis. And Girfan-Zeitlin basis is given by some sort of diagrams, but if you are looking what kind of diagrams are here, maybe I do not want to explain, because if I do, I will make mistake and so on. But the answer I remember that the Girfan-Zeitlin basis in this representation, combinatorially the most natural parameterization are plane partitions. So plane partition, we put some boxes here, here, and here, and so on, and they are some parameterization of a basis in this space. And the point is that this basis can be determined in terms of this J infinity or in terms of differential operators, and so it is fine. But important story is that this basis can be deformed. And actually W-algebra also has a natural basis labeled by the same date. Now, this basis is the basis which people, AGT people, or Nakajima himself and other, because geometrically this basis is connected with fixed points on the modular space of something. But the best way to understand what is this basis, just think that this is version of Girfan-Zeitlin basis, and so this is it.
But Boris, standard partitions somehow are one-to-one, but not these partitions in the space, right?
No. Plane partition.
Plane partition.
Plane partition. Where you
No, the plane partition is this.
Yes, please.
No, plane partition, you have this corner of a room, and you put.
Instanton sum is a summation over partitions. Standard partitions, how to say, in plane, right? You have space picture.
No.
What is this picture?
No. Instanton sum is a sum over the object like this. Not plane, by plane partition, not Young diagram. No. Usual terminology is the following.
Yeah, I agree with you, right? But not that, according to my understanding, the Taker formula is given in terms of just partitions with Young diagrams, right?
No. So we take it means no. You are right in the following sense, that it depends in what representation we are talking about. That if we put here integer, then if this integer is positive, then it means that our highest weight is still dominant. And in this case, the description of the basis is in this case, this representation, so because n is integer, then we can factorize it and get smaller representation. In this case, the corresponding smaller representation basis is also plane partition but the height of this plane partition is n or smaller. For example, if n is 1, then it means that this plane partition is living on the bottom.
Reduction to 2 parameters.
Yes, and so what we take a vector with what we are talking about corresponding to n equal 1.
And what is we take a vector with all 3 epsilon 1, epsilon 2, epsilon 3 parameters, right?
No, in this business we will have only 2 epsilon 1, epsilon 2. Epsilon 3 still is not here. But maybe I want to say one word about representations of J infinity, which is also rather simple. If this number is negative, then corresponding representation is highest weight is not dominant. But in this case, such representation still has Girfan-Zeitlin type basis. And it's also labeled by Young by plane partitions, but now we have to do the following. We have to find on the bottom the point NN. And then write down the partition.
But your one-to-one corresponds with all plane partitions was even for complex key, for arbitrary, generic key.
For generic, yes.
For minor sense, it will be something smaller, right?
Now, smaller it means that representation depends on lambda. And if lambda is generic, yes, if lambda is generic, it is irreducible. No, and this special representation is reducible only if n is integer, because we are living in the most simple situation which is possible.
I don't understand. If you have definition of W for arbitrary complex K, why you need these reductions? You don't need them at all, right? You're already done. If this algebra really exists for arbitrary complex K, W, and right? Then is the end of the story for my view. Why you need delicate reducibility or whatever?
No, but first of all, the representation of this algebra it is interesting by itself. If you are asking about why you need construction of reduction, that the answer is that I want to connect the representation of algebra J-hat with the representation of W-algebras. And this is an important point in both directions. One way the knowledge about representation of J-hat gives us information about the principle of reduction, and opposite is also true.
Instanton sums has no immediate connection with GLN. They just instanton sums, right? So from different stories about C2 or whatever, right? And then if you have finally, it is even better if W depends on complex number, because then this third parameter and things are only nice, right? Wrong?
No. No, if you're a person who deals with geometry, I think what you are asking is the following. Well, we are playing with J-hat and make up the reduction. Reduction is something, what is, wait, let me finish. Reduction, this is something what is acting on the K-theory or homology of these instanton spaces and so on. J-hat itself is also acting on the modular space of some different objects. Then, so in some sense, it means that J-hat or W-algebra and all reduction in principle, it is not known in a full range, but they're acting on a modular space of some objects. Yes, and no, this is geometric fact which extensively using. What you maybe what you are asking that we have on the level of W-algebra the construction of reduction, which using JLN and gives us W-algebra. The correct question was what does it mean from the point of view of geometry? What we make up.
We count instantons without any reference to any n. we just count instantones, right?
No. If you count
parameters, but instanton parameters, right?
Yes.
They are not immediately connected with GLN or whatever.
they are connected. They are connected. There are some parameters. GLN. This is what kind rank of representation of sheaves there, and parameters. Other parameters are related with equivalent.
Not directly, right? Because eventually the summation will be over all Young diagrams, right? Absolutely all of them, right? Which means that there is no fixed GLN whatsoever, right? Something different. Okay.
Anyway, but I want to say something which seems important, that if n is negative, then the basis in this representation I given a plane partition which does not contain the point n and n on the bottom. So if for positive n partition, plane partition are living in such part of my corner, in negative n, they are living in such part. So it does not contain this. So they are living along this wall and along this wall, but not far. The distance is not bigger than n. Yes, and the interesting business about the character of such type of partitions, in this case, maybe not so complicated, in the other cases more, but anyway, basis is given by this. And one more thing is that at least I, and maybe Nakajima-san also, he doesn't know the geometric picture where fixed points are just labeled by these things. It has to be related, maybe you see after some time, with super algebra JLNN, but it is some kind of conjecture. But is it true, or I don't know.
You mean you're doing vector bundles of negative rank in a sense?
Yes, but negative rank is not good. So
yes, I understand.
But nevertheless,
no,
yes. In some sense, we wanted to consider this and just shifts shifts can have negative dimension if
in complexes in the business.
If business is in complexes, but such approach I think doesn't work. We have to do something else. Anyway, it is not known. But again, combinatorial, so it is this, and then.
Can you say what is happening if a point n? What is the representation? If it is inside this.
N.
Yes. If you want to solve all diagram.
No, again, the geometry is not known, but there are some speculation. But if you are talking about Lie algebra, then no, the representation are just this. But if you look deformation, if you have a W-algebra, then in this case, for some combination of parameters, it has a representation where basis is labeled by partition which does not contain the box with number n, m, k. Even more, that it is the conception. No, maybe you heard that in Yangian theory this is a conception of twisted Yangian. And if you take twisted Yangian, it has more interesting, more rich at least representation. theory than usual Yankean. Here you can consider distort a little bit this W algebra and consider some strange object, which is not well studied. In this case, basis can be labeled by playing partition with more conditions. For example, why not take 2 points somewhere and looking for partition?
In instanton picture, there is no support for this. There are only 3 parameters at most, right? No, nothing else. Because you can put any K, K1, K2, K3, or whatever, right? You have some crazy questions, right? But at least these questions are not because of the No.
First of all, some of these questions are crazy, some of them not. But I think that from the point of view of geometry, you have a lot of modular spaces. Instanton modular spaces, and you can consider instanton modular spaces, for example, with parabolic structure of many different kinds, and Lamont structure and partly Lamont structure, and this is not all. So, in principle, this topological theory and corresponding modular space, you have a lot of different types of modular spaces, and something is acting on cohomology of them. So we have big freedoms here. Yes, let me say a few words about what as W-algebra, just this W-algebra, it is not the only construction of this. We can do more things. One thing is the following. We can take Gaussian hat of level K and consider the construction, the name of this construction is cassette construction. What is this? The simplest cassette construction is following. I can take Gaussian hat and I can take Gaussian -1 hat, and cassette, it means that not very precise definition, because it is not, sometimes it is not working. But you can take Gaussian hat and consider the subalgebra here. Here, which commute with JL and -1. No, it is something, and such kind of construction you usually need if you take the representation of bigger algebra restricted to smaller algebra and want to control the multiplicity after restriction. And the representation of cassette algebra just do it. It is acting on the multiplicity of restriction, on cohomologies also, and on things like that. And so what kind of algebra here do we have? No, I wanted to say here the following. So if you first of all answer, and after answer some speculation. Yes, and speculation of what? That as a result, we get W-algebra, just the same W-algebra, what I determined, but with some parameters.
Yeah.
No, first of all, here we have two parameters. One parameter is n, and other parameter is level, k. The W-algebra which we get is corresponding to k. So this is some incarnation of level around duality and things like that. So now here k is integer, is not integer, it can be any. So as a result we get algebra where these parameters become complex, but still something here is integer, and this is integer n. And this is what? I said that in W-algebra we have K and also C. But C is better to characterize in terms of these parameters P and Q. And these parameters P and Q, they are n plus K and n plus K minus 1. So it means that the essential thing is not P, Q, but ratio. N plus K over n plus K plus 1. And so now I'm saying that we get the same W-algebra, but it is some strange playing with the parameters. Now what was before n, now it is K. It is not this n at all. But what?
Is it really okay if k is not positive integers or arbitrary in this business? Non-integrable representations for this construction?
No, here non-integrable representation also can be used. If we define cassette algebra, always possible. We can do it without problems. And to define the cassette in big generality. And
still, naturally, k is still a positive.
No, not necessarily. It depends what kind of program you're looking. It is not necessary.
Then there will be great jump of the size of the corresponding commutant, right? If it is not integrable, right? So it can be much bigger.
No. No, the situation is general that if you have just algebra E and algebra B, and you are asking what is commutant here, you understand that for generic associative ring, such kind of problem also is ill formulated. If you want the define of pair A and B, so before, for example, I take A and B and define Bldg algebra, I induced, it did something. No, this construction is good to understand, but maybe it is not for calculation and for real definition, it is not very good. But now the situation is similar. I have similar in the sense that I have pair A and B, and I want to determine the commutant of B in A. If you want to understand this as a functor on pair of A and B, then actually you need to define it in corresponding derived category of DG or simplex. No, just like this, it is not very good. Anyway, but in examples, usually it is possible. No, general definition is not good. But usually in examples, it's more or less working, and it is working. That you can not necessarily key integer arbitrarily, and you can write down generators explicitly if you want. It's possible, and you get some algebra which really depends in n and k as a parameters. And by the way, we also can make up analytical continuation in n in this case. And if we are talking about integrable representation, then in this case, with this algebra, commutant is something happening. It appears some ideal, and you factorize by it. It is singular point for that. But it does not. But the algebra itself exists in general, and so no problem. And I said that, first of all, I said, what is this? And maybe one more thing, that actually what we expect. In some sense, we cannot expect this. But construction is if you have just universal enveloping of JLN, and if you take universal enveloping of JLN minus 1, and you are looking...
Well, you're trying to explain the answer, right?
No, I trying...
Analyze it.
No, I want to speculate a little bit. Just
concerning this particular answer, it is different.
No, I like speculate, but right...
Concerning what? Speculate concerning...
About this answer. If we take universal enveloping JLN, and universal enveloping JLN minus 1, and then suppose we are asking about the same question. So what is the commutant of this here? Now we know what is this. We have center here in a big algebra, and we have center in a small algebra. And the commutant is generated by two of them. Center of JLN, center of JLN minus 1. Yes, and so and this is commutative algebra, and this is the reason why restriction of the irreducible representation of JLN to JLN minus 1 has a simple spectrum. So what is going on here? We're just trying to affinize, make affinization of this. So I put cap here, I put cap here, and just want to ask what is this. And what we expect is what? So here we have some generators, here we have some...
GL1 hex, what will be your destination, right?
No. I'm talking about what I'm talking. So it is this. So anyway, the result of our activity expect to be affinization of what is going on here. Yes, and no. First of all, it gives us some hint, but just as it is wrong. So it is the result has some relationship with this, but it is not this. No, because here we have Casimir here, we have Casimir here, we have also two cubic Casimirs and so on, but our answer is not like that. So it is not precisely this, and no, again, for a center on a critical level or about the Hamiltonian reduction, what I explained, such kind of speculation at least good hint what is going on. Here, not. But nevertheless, answer is this, and then let me say.
But systematically, if you consider these commutants, it is a double Youngian or a toroidal algebra, right? And then toroidal algebra, of course, connected through Daha, connected with stuff like this. It's like diagonal coinvariance. And more or less directly you reproduced the classical case of representations of double fine Q, which is expected to appear here because you are doing Kac-Moody and Kac-Moody, not just algebra and algebras.
One, yes, yes. So
almost certainly I saw this formula exactly on plus K. I can explain it after the lecture where I saw it.
No, you mean such kind?
Exactly, n plus K plus.
No, maybe, but maybe about what you said, that we know that if we take universal enveloping of JLN, and if we take universal enveloping of JLN minus K, and suppose we have such embedding, then the question, yes, the question is standard and old Alshansky type question that what algebra here commute with this. And the answer is what? Here we have, what is the answer? Here J is K, here JLN minus K, and what part which is commute? So first of all we have EIJ which is here, then we have EIJS times SIJ, the sum in S, where I and J is still here, and S is running everywhere, for example, only here, and also EIS1, ES1, S2, ES2J. So I J fixed and summation is going over all this, and this. And standard invariant theory says us that really the commutant of this in the whole thing just generated by these elements, and we can identify with the known algebra, which is Youngian. It is Youngian, and it means that we have, for example, this, which looking like JLK, we have this, which is looking like second copy of JLK, and here is the third, and so on, and this is really looking as one half of Kac-Moody, but with distorted relations, yes. Anyway, what we are talking now is the affinization of this construction. We can put here and here caps and ask what it gives us, and it also will be some interesting algebra, and the name of this, no, it is some incarnation of double affine Youngian. And double affine Youngian people are, well, usually it's appear in a little bit different content, and so it described because of this in a little bit different generator. But it is this. Yes, and so anyway, by this way, this is construction of some vertex operator algebra, and I discussing only the case where it is this, and so from this approach, this incarnation of W algebra can be understood as JL1 J1 hat Youngian, and so this is yes. Now about the character again. So no, well.
Just one remark. N plus K. It is classical formula for the central charge, which is N from roots of unity plus dual constant number, right? This is more or less N plus K.
Yes, I understand. what you are talking. Yes, and I wanted to say the following, that, well, that if you take this algebra, I mean, suppose better to take, so again, Jn hat by Jn minus 1 hat. Yes, then this is such algebra, and again you are asking, this algebra has vacuum representation, some basis in this vacuum representation, and our knowledge says us that, well, it means that some kind of Gelfand-Zeitlin like basis in this representation have labeled by plane partition, and this plane partition is following. We have to put here in the bottom a point n minus 1. So I explained that before we had point n. Now we have a point n minus 1. And all partitions which are living here give me the basis in the corresponding representation. And for example, let us look some example. We have some not very complicated but non-evident formula. Suppose n equal 2. Yes, and if you have this cassette, so it means you take GL2 hat over GL1 hat, or this is the same as SL2 hat over SL1 hat, which is more or less nothing. And but what does it mean? It means that vacuum representation of the corresponding quotient, to get it, we have to take the following. We have to take SL2 hat for generic K. Yes, and we have to take vacuum representation for this. And vacuum representation is what? Highest weight vector. Then we have SL2T minus 1. Then we have more vectors, and vacuum representation of this quotient is the part of this where the operator H0 from SL2 acting by 0, so it is just this. Yes, so it means that the character of all this space is what? It is, first of all, this character of SL2 hat, and it has Q grading, it is this. And this space are polynomials. What is SL2 hat? SL2 hat, this is SL2 times C, maybe T inverse, and so if in SL2 we have basis EHF, then here we have basis AFI, HI, and EI, as I said, I belongs to Z. And this representation is what? These are polynomials, Poincaré-Bergov says that they are polynomials in EI, HI, and FI, where I is negative. Therefore, what we have? We have character of this. We have Z grading, where this is 0, this is 1, it is minus 1. And Q grading by I. So the standard formula for a character, it is what? It is, we have 1 minus ZQ, 1 minus ZQ square, and so on. Then we have 1 minus Q, 1 minus q squared and so on. And then we have 1 minus z inverse q and 1 minus z inverse q squared and so on. Now, this is such kind theta function type expression, and so this is contribution of E, this is contribution of F, this is contribution of H. And then we take coefficient in front of Z0. Now, it is something, and they're not very complicated, but rather the interesting fact that what combinatorial data are counting the coefficient in front of Z0. And the answer of this kind is following. We have to consider again the corner of a room. Then we have here the point 2, 1. And consider the plane partitions which are living here. So it means that along this distance is 2, this distance is 1, and they are living there. And you count just the generating function of such partitions. So just write down the sum of q, g, and here is number of partitions with such restriction in G boxes. And so I claim that it is just coefficient here.
You claim or it is classical?
No, it is no, because it is not so complicated. It cannot be very new things, but yes, but the fact that it is connected with the partition of such strange kind, it can be maybe known, but I do not insist.
But do you have formulas for arbitrary, for SLN, for the heads, for instance, of the same kind?
Yes.
So still playing partitions?
No. Yes, but we have to be accurate. For SLN, more complicated.
Yes, but no, right?
No, but yes. No, I can explain, but maybe not now.
Is it special? I mean, exact question. Is the appearance of plane partitions is a special phenomenon for SL2 head or some kind of more general?
More general. No, but well, I said, for example, that you have the situation JLN hat over JLN minus hat. The multiplicities, you take representation of
always
this.
N minus 1. Always.
You take representation of this. Maybe even vacuum representation. You restrict it to this. And multiplicities are counting by plane partition with some condition. Yes, then in principle, if you want to say something about base here, you just need to continue from JLN to JLN minus 1, from JLN 1 to JLN minus 2.
Pairs, triples of partitions,
No, it was some sequence of partitions with some conditions, and they are not completely unrelated. So if you want to formulate it, it is possible, but you will not be happy.
Boris, so SL1 head is what? It is trivial or Heisenberg? So SL1 head. You divide SL2 head by SL1 head, right?
No, SL1 head is nothing but...
nothing but or Heisenberg. So
no, it is
nothing.
No, SL1 head it is nothing. Yes. But it's better, not?
Well, it's okay. Nothing is good. I like nothing. But
yes.
No normally cassette models, you know very well, we are supposed to divide by Heisenberg as well, right? But this is GLN story, right? This is GLN, right?
Yes. And maybe...
So conjecture is that if it is this OR fact, if it is SLN divided exactly by SLN minus 1 hat, right? Then planar partitions, some planar partitions will, plane partitions will surface, right? Conjecture effect, what is the status?
Say it again.
If it is exactly n minus 1, what's that? But then mysteriously plane kind of partitions will appear.
Yes.
Is it some kind of statement which is maybe published or whatever, right?
Published, yes.
Published and what? So some reference for this.
No, we have, first of all, we have some papers with Jim Muhin maybe 5 years ago or something like that, where such kind of thing started, and maybe more than 5 years. And we have some more recent paper, which is still not published in the archive, but for 2 years maybe now, with Misha Berstein and Grisha Mirzon, where for partitions of such kind are written the character formulas. No, well, no, what's the problem? Problem is that this is an object, such kind of partition is a character of representation of some algebra, some W-algebra. If you study W-algebra, then our experience says us that for representation in many cases, it has some resolution in terms of beta representation, which is like Fermat. And therefore, for such kind of things, we expect to have a sort of wild type formula. And if we do not expect the things like Cardan-Lustig, where coefficients are complicated, in this case not, that it means that we can try to find what kind of wild type formula is true.
But this is for W-algebras. You use W.
No, W-algebras in principle, the theory of W-algebra is not developed enough.
But you mentioned you mentioned this WK or for some special P and Q, which you gave this.
No, if you're just talking about WK, it is fine. In this case, we know about the existence of Bernstein-Kirfan type resolutions and so on. If you are talking about W-algebra with more complicated connection of parameters, like here, what was written here, and I erased. It is not so standard, and we cannot find for W-algebra the precise way to construct these Bldg type resolutions and so on. But
the paper you mentioned is about W-algebras or about this cassette model?
No, the paper, last paper which I mentioned, there are some kind of information about W-algebra, yes. But main content of this problem is pure combinatoric. So it means that somebody, me for example, give you this space of plane partitions and ask what kind of wild formula is some alternating some simple things which you can write explicitly what is this. And it is some technique how to get these character formulas, and so the structure of a paper that it is possible combinatorially to get such kind of formula and formulate conjecture that such kind of alternating sum are corresponding to Bldg resolution. About the construction of Bldg resolution, in many cases it is absolutely unknown how to make up them.
Bldg for what? For heads or for W?
No, for heads it is known. After many people, Kashivara and so on, it is known. Or if we make up the reduction, it is also known by Arakawa-san, but maybe not in all cases. In many cases, it is known. But for example, maybe no, I can say many things, but now it is time to stop. Anyway, we can infinity. Well,
you seem okay. You seem okay. You can continue. Are you okay?
No, I am yes, but the people die soon, and
you're a boss.
no, I'm not. I'm not. I'm a slave. Okay, but let me say only one thing that they are a construction of W-algebra. Let me just mention, it is not only that. It is also popular construction of the following type. I can take GLN. I can take representation of level 1. And I can, let me denote this representation, say by this way. And I can take some irreducible representation of generic level. And then try to decompose it with respect to diagonal action. Then, as usual of such kind of problems, this is also the problem of finding commutants. But now it is something acting here of level 1, something acting here of level k, and then diagonally here is acting level k plus 1, and then we decompose. And interesting by the algebra, which is acting on highest weight vector, on in multiplicity space, and so on. The answer is it is third construction of the same W algebra. So if you just look what is this, it will be algebra where again parameters are no, it's also some playing of a parameter. So it will W algebra with the same n as here. But central charge or other parameters p and q, they can be found from this. And one more thing.
You mean the commutant of the diagonal embeddings of what classical definition of Virasoro, right? So
yes.
This line, right? Virasoro is S into head, and it invariant with respect to the diagonal embedding, right? This is what you are saying?
Yes. And one more thing, that it is some kind of direction of studying, maybe natural, maybe not, but in all such things we can, considering in all these places superalgebras. So what does it mean? For example, we can take Gn and M hat and make a reduction over Gh n minus 1 m hat. And just ask what kind of algebra we get as a result. It also will be the same algebra, but now parameters depending in n and m. And in this case, the character just given by plane partition where some box is not admittable, which is not on the bottom, but somewhere depending in n and m. And in all cases, you can do, for example, here, you can also, considering GLNM, and make up the same business, and taking GLNM has also some notion of fundamental representation, even two types of such representations, and you can do it, and again, the same
Boris, so why not instant W-algebras? We just want to solve this particular problem, to calculate the character, right?
No, we can.
And to see which partitions, blank partitions appear there, right? Or something like this.
No, there are two. No, again, there are two things that you can make up reduction and study corresponding W algebra, and the question when you can explicitly describe it. Actually, it's not so many cases, and most cases when you can do it, this is some special case of our W algebra, depending in n and k for some specific choice of parameters. There are a few other cases, and so at least for many reduction problems, and I mentioned not all of them, but maybe almost all, we get the answer like this. Yes, but and also the basis is in the representation of in this cassette business of this W algebra are given by plain partitions. Yes, from the representation point of view and from representation of geometry, actually we need much more. But we can. Okay.
But still, do we have some name for this commit, and it's connected to some kind of super algebras, Schwarz, whatever? What is this?
No, we can, yes, for some special, and then we.
Super story.
No, it's a super story, yes, but.
Do we have some Schwarz generalizations of W algebras?
No, we have, and it is some amount of generalization of all what I said. No, it is just a question that what is actually exists. So I said that we have polynomials in the inverse, and we consider the differential operators which is acting here, deform and doing something like that. If you put here one odd variable, for example, then we have differential operator in this Z and this. Yes, and if you are talking about this super Lie algebra and about the deformation of this, all such things exist. It is known that they exist. Something is known about this, but not much. So here it is. To describe this algebra, many questions. So this is a subject which is very easy to ask questions. And for me, it's easier because I know more. So, but to answer...
The more you know, the greater the number of questions, right? So let's stop now.
Yeah.